All right, function folks, this is part two. First part was on piecewise functions, and the second part is on operations on functions. Again, the idea here is, what are some things that we can do to make our models a little more complicated, a little more, what's the next step with functions, and we'll see that today's part, or second part, is on combining functions in some way, and this is it's actually quite natural what we're going to be doing here. So we'll just follow along the example, and we'll see what the story is. The first question is to find h at x, which is equal to f at x plus g at x. So this is a new function, h at x, which is just, whoops, f plus g. Well, f at x is just this line 2x plus 1. G at x is this parabola x squared, just the basic parabola. And then together then, if I want to write them in the right order, it looks like h at x is some sort of parabola as well, but we'd have to complete the square or find the zeros or do all sorts of strange things to figure out what that is. Part B here, oh, by the way, we actually use some notation to show what a sum function is. Sum function. Normally we'd write h at x is equal to f plus g at x. And it's exactly what you'd think, the two functions added together. So just notation-wise, we consider h at x this new function, sum function. It's the sum function. And whoops, and you can probably guess what the difference function would be, right? Or in part C, we'll see it's a product function. All right, dandy. So just a little bit of notation. This idea, when I see f plus g at x, I know that I'm just taking the two functions, f and g, and adding them together. B, in part B here, we want to graph the three functions. So I'm going to graph them. F at x is 2x plus 1, which is a line with slope 2 over 1. Y-intercept is 1. Watch my scale here. Notice that I'm letting each tick in the direction of x be a half, and each tick in the direction of y be 2. So my scale might be a little bit different than yours. You can do whatever you like. Y-intercept of 1, then a slope of 2, up 2, right 1, up 2, right 1, up 2, right 1, and then same thing the other way, down 2, left 1, and I can get, this is my graph of f at x. That's f at x. And g at x, I'm going to do in a different color, is the basic parabola. And watch my scale here, right? Over 1, up 1, it kind of looks weird. It'll look like it's squished, but that's just my scale. Over 1, up 3. And there's g, which is this basic parabola. That's g at x. Now, for h, certainly we could use all of our grade 10 methods and grade 11 methods to graph that. But if we just think for a little bit here, what h at x is f and g added together. I could think of it, if I wanted to, as a table, right? For my x values, I got f and g and h, right? So, and I'll list a couple here. For x is minus 1, 0, 1, and 2 maybe. What are my f values? Well, these are all the purple values, and I could calculate them, I suppose, but I'm just going to read them right off the graph. Negative 1, it's negative 1. 1, 3, and 2, or what was that? 5. And for G, it was 1, 0, 1, and 4, right? basic parabola. And what's h? Well, h is these two things added together, right? So I could think of it as negative 1 and 1 is 0, 1 and 0, 1, 3, that's 4, and so on. I could do it this way and just graph these points. Now, what I want to mention to this, I don't even need to do this because essentially these values f and g are on the graph. If I think of, all right, the green point plus the purple point is going to give me my new graph h, which is the sum function. It's just going to be this plus this negative. It's going to be right there. I think of now I'm going to go over to the next point that's got both values there. Green plus purple is 1. 1 plus 3 is 4. And you see what I'm doing. I'm just adding the individual points together. I'm going along for each x where I have nice points. There's green is 4, purple is 5, add 9 is going to be up here off my graph. And in fact, there's my h at x. I can do it graphically. I don't even have to think of this table. This is h at x, which is equal to f plus g at x. And all I did is I added the individual outputs. So in part C, we're going to have another go at this, except for part C, and maybe I'll do this in blue, is a product function. Part C, j at x, which is equal to f times g at x, is a product function. When there's no operation in there, it's understood to be a multiply. And instead of actually doing this or doing the table, I'm just going to think about going along, and instead of adding the two together, I'm going to multiply them. So each input, so an input of -1, I go +1 times -1 is -1, and I get a point on j. Then I go 0 times 1 is 0. 1 times 3 is 3. And these are all points on j, this function j. Now I go 4 times 5 is 20, way up. So it's going to go up very quickly. And in fact, these are the only points I'm going to get on there. Notice that this works not only for nice points, but for any point. So for instance, this would be a half times 2, which would be around 1. And I think right in here there's an important point, because there's a 0 there. 0 times whatever that is for the green one is going to be 0. So I can actually add a little more detail to this blue graph. Kind of looks like this. We said it goes up really sharply. And we've never seen a graph like this. This is a little bit crazy, this one. And it's the product function. I'm interested, just because we've never seen a graph like this, what its equation might be. And what would the equation be? Well, f was 2x plus 1. G was x squared. And if I multiply that out, I get 2x cubed plus x squared. X cubed, this is a cubic function. We have never seen a cubic function. In fact, this is one of the things we'll talk about in Unit 1. We've never seen that before, even though we were able to graph that using the graph. So that's pretty neat. One more example, and this is kind of a strange one. We've got two functions, and just a few points are listed. We don't know what the equations are. We just have these points, and we want to. This is a difference function we want, right? So we've got g minus f at x is essentially, we could think of it as g at x subtract f at x. But what's weird is we don't have any equations, right? There's no formulas here. We just have the points. So in fact, our difference function is just going to be a list of points. Well, what list of points? Well, notice for each input, I have to find the point where the other function is defined as well. So for instance, an input of 0, what's going to be my output? Well, I have g minus f G is 0 and F is 1. So 0 minus 1 is minus 1. And how did I get that? That was because I had G minus F. And in that case, just like I did on the graph, I'm looking for, when X is a certain value, 0, what are the Y values for each of the two functions? Now notice the next input of F is 2. I don't have a 1. But what's the output that goes with this one? Well, an input of 2, an input of 2. So now I'm going to have my output is, so my difference function is G minus F 1, 4 minus 3. That's where I got that from. So, well, what happened to this point? Well, there was no point on F that has an input of 1. So I ignore that. It's like F was not defined for this input of 1. There's a gap there, so I can ignore that. And actually, similarly, here an input, I'll go to my next point for F, and I have an input of 4, but G's got no point defined there, so not defined. And in fact, same thing for 3. The only place where both functions were defined were at x equals 0 and x equals 2. So that means we're done. All right, the homework actually covers 2 chunks in your textbook. So there it is. And the FAQ, I think, is, I can't remember whether it's a PieceWise function or an operator, probably one of each. Probably it's a little bit bigger of an FAQ today. And good luck with your homework, folks.